Ruth. Welcome to the lesson on optimization. And when we talk about optimization, we're just solving a bunch of word problems where we want an optimal answer. So let's look at this one. A man launches his boat from point A on a bank of a straight river, 3 kilometers wide, and wants to reach point B, 8 kilometers downstream on the opposite bank, as quickly as possible. If he can row 6 kilometers per hour and run 8 kilometers per hour, where should he land to reach B as soon as possible? And so looking at some choices, he could just row from A straight to B. This might be the worst possible option because he's rowing a very long distance and he's pretty slow when he's on water. Another option is that he could minimize his rowing distance by just cutting straight across to point C and then running the 8 kilometers. So when he runs, he's pretty fast, but if he goes directly across and runs, this is a very far distance to run. So the optimal solution is going to be something in between, all right? And when we look at this problem, it says as soon as possible. So we are trying to optimize total travel time. Okay, in other words, and optimize in this case is to minimize total travel time. Okay. So when I look at this, I'm going to look at some relations here. And so I'm going to say let's see that he rows to some spot here on the bank, and then he runs the rest of the way, okay, to some spot here. And this spot here is variable. It could be right here at point D. It could be point somewhere along here, anywhere. Okay, but I'll call this distance D1, and I'll call this distance here D2. Okay, and now we're going to set up some relation between D1 and D2. So let T equal total time. So T then is equal to the distance in the water divided by how fast he can move in the water plus the distance on land divided by how fast he can move on land. Okay. Then what I'm going to do next is see how we can rewrite one of these distances in terms of the other. So we can make a little right triangle here. This is 3. This length right here is 8 minus D2. Okay. And so that tells us that, let's see, D1 squared is equal to the square root of 9 plus 8 minus D2 quantity squared. And that's just using the Pythagorean theorem. Oh, I'm sorry, not D1 squared, just D1. Okay. So then we're going to make the substitution now. So T is equal to D1, which is the square root of 9 plus 8 minus D2 quantity squared, all over 6 plus D2 all over 8. Okay. And then from here we're going to try to minimize T. And to do that, we're going to take the derivative. So this is 1/6 times 1/2. Okay, because the square root here is just raised to the 1/2 power, times 1/2, 9 plus 8 minus D2 squared, all raised to the negative 1/2, times the derivative of the inside function, which is 2, 8 minus D2, times the derivative of negative D2, so there's a negative here. Okay. All of this plus the derivative of D2 over 8, so 1/8. Okay. So this negative here is going to just flip the sign of 8 and D2, all of that is going to be over the 1/2 here, and the 2 are going to cancel. So this is all going to be over 6 times the square root of 9 plus quantity 8 minus d2 squared plus 1/8. Okay. Then next we are going to find the point of t where it has a tangent of 0. So we'll set this whole thing, this big mess here, all equal to 0, and we'll solve for d2. Okay, so subtract 1/8 from both sides, multiply both sides by this denominator, and so this is going to give me 3/4. Alright, and then we're going to square both sides, so this will give us 9/16 times 9 plus 8 minus d2 quantity squared equals d2 minus 8 squared. I've distributed the 9/16 to the 9 and 8 minus d2 quantity squared. I've multiplied out the right hand side, and this is what I get, and just keep simplifying a little bit more. Okay, I think I've made a slight error here. This 15 is supposed to be negative 16 plus 9, so this is supposed to be a 7. Okay, but other than that, that's correct. And then this is basically a quadratic, so I'm not going to go into solving quadratic. So solve this your own favorite way, and once you're done with that, this should be the answer. Okay, so this is your answer, and this is about 4.598 kilometers. Okay? Which means, looking back at the original problem, the person who's rowing here should row to this point such that d2 is about 4.598 kilometers. Okay, and we should also check this as well and see that this is in fact a minimum of the original function. So we can certainly do that right now. So here we look at t prime, and if you put a number, you can see that the bottom here is always going to produce a positive answer. So all that matters here is the top compared to 1/8. If you put a very large number in here, say like 100, then the top is going to be positive, and this is also going to be positive as well. And if you put a very, very big negative number in here, say negative 100, then this top here is going to be a very large negative number. So this here is going to be a negative. So this means you have a minimum at this particular point. Okay? And so if you look back at this problem, there's a lot going on here, but it comes back to a very fundamental idea, which is look at the situation, draw up some pictures, try to relate some of these variables together, and then the optimization doesn't really come into play until we start to use this function. And at that point, we're really just taking the derivative and determining where the derivative is equal to 0 in order to apply the first derivative test. Well, thank you for watching. As always, if you have a hard time, ask your teacher. Have a wonderful day.